Today, we're joined by Professor Armando Solar-Lezama, Distinguished Professor at MIT's College of Computing, Professor of EECS, as well as an Associate Director of CSAIL. Originally from Mexico, he earned his PhD at UC Berkeley, where he created Sketch, a groundbreaking program synthesis tool. At MIT, he's leading the Computer Assisted Programming Group, advancing program synthesis and Neuro-Symbolic programming to blend deep learning with symbolic reasoning. As the recipient of the 2024 Robin Milner Young Researcher Award, he is a leading voice in programming languages and envisioning AI as a partner that empowers developers and fuels scientific discovery. Professor Solar-Lezama, it's a pleasure to have you on this AMA. And to begin, can you briefly explain what program synthesis is?
Sure. So, first of all, very happy to be here with all of you. So, program synthesis is all about how do we get machines to help us write code, and in particular, can we get machines to do more than just what compilers have traditionally done for us, right? Simple translation. Can we actually get it to help us with some of the more intellectually challenging aspects of writing code, from figuring out algorithms to just helping support the programming process?
What was the initial spark that led you to pursue program synthesis? Like, was there a problem with traditional hands-on programming that you wanted to innovate on, maybe?
Sure, sure. So, if you go back to all the way back in the early 2000s, when I was just starting out as a graduate student, I actually started out working in high performance computing. And one of the big challenges at the time in high performance computing was that you wanted to run these computations spread across thousands of CPUs, and you had this very peculiar challenge where something that, if you were to write it just as a sequential algorithm, you could probably write a version in 20 lines of code. But when you have to run the thing on a machine that has distributed memory spanning hundreds of nodes, those small numbers of lines of code balloon to hundreds, in some cases even thousands of lines of code. And so at the time, there were a lot of people working on compiler solutions to this problem, right? And can we develop better languages to help simplify the problem of programming these very complex machines? But right around that time, some really interesting developments happened in the space of formal methods and program analysis, where suddenly it was starting to become feasible to automatically find bugs in programs, to automatically discover vulnerabilities. And there was a lot of excitement in the community around that kind of technology. And that led my advisor and I to start thinking about, hey, could you actually leverage some of these new technologies, not just to help you find bugs in the code that you've already written, but help you write the code in the first place? And so that was really kind of the initial drive to try to address some of these very challenging programming problems by leveraging techniques that had originally been developed just to help people find bugs in code.
Wow, that's very interesting. So can you elaborate on some of these projects that you have done with the group at MIT, and then some core philosophies that you always try to follow inside of these projects?
Sure. So we've been working in this space now for I've been at MIT for 17 years. If you count my PhD, been working on this problem for almost 20 years. One of the big things that we tried to do from the very beginning was to look at how we can leverage large amounts of compute in order to help with some of these challenging development problems. But realizing also that you don't necessarily just want to replace programmers, right? You want to have users and developers in the driver's seat. And the whole point is to complement what are the skills that the developers bring to the table and combine them with the kind of benefits that you can get from large amounts of compute, right? In the beginning, a lot of the early projects that we did focused on search-based techniques and algorithms for searching very large spaces of candidate programs in order to find ones that actually satisfied your specification. And then around 2013, 2014 was that we started experimenting with deep learning and with combining some of these search strategies with learning. But at a high level, an important aspect of it has always been to think about this from the perspective of a collaborative approach between developers and the people actually and the algorithms themselves. For example, our early system that we developed for this purpose was called Sketch because the high-level idea was we want the programmer to bring to the table their high-level knowledge and their intuition about what a solution might look like. But then we want the synthesizer to figure out the low-level details, right? The tricky, fiddly, low-level details that often are hard to get right, where often the programmers don't know them off the top of their head. They have to actually sometimes even get out pencil and paper to figure out those details of the algorithm. So we want the machine to figure that out, but we want the system to be able to leverage the things that the programmers do bring to the table: high-level knowledge, high-level requirements about what they want the software to do. Nowadays, with learning, it's actually been very exciting to see how a lot of these technologies have matured. Right in the early days, the very first project that we did that actually involved deep learning to essentially learn how to generate code. We trained it with a few thousand solutions to programming problems that had been created by students using who were taking an introductory programming course in the edX platform, right? And these, at the time we were really excited, like, wow, we have access to this huge data source, and if you compare it with the kind of data sets that are available today and the kind of models that we can train today. But it's actually been very exciting to see the evolution of that technology and the really exciting things that it can do today.
So my understanding, like the difference between a program synthesis approach and like using a large language model is that with program synthesis, there are these like mathematically verifiable sort of guardrails on the output of the program synthesis, if I'm like explaining that correctly.
So in general, yes, that has been a really important focus on from the program synthesis side, having strong guarantees over the outputs because a lot of these techniques arose from the capabilities that we had around doing automatic bug finding and eventually around doing full formal verification. There was this co-development of verification techniques and program synthesis techniques. But we tend to use the term more broadly. For example, one of the big success stories from the program synthesis community was in the space of programming by example, for example, and programming by demonstration, where you want to be able to generalize from individual instances where the user says, well, for this input, I want this output to happen, and for this input, I want this to be the output. And from that, to be able to actually explore the entire space of programs and be able to generate a program that matches those inputs and outputs. But in general, there has been a very strong emphasis on strong guarantees. For example, even in the context of some of these program by example setups, there is an emphasis in saying, well, I don't just want to kind of produce these outputs, right? I want to exactly match this input with this output. And if it's truly not possible, I want the system to tell me, no, it's not possible to match this input against the output, right? I don't just want the system to do its best effort and give me a solution. I want it to actually tell me that there is no possible solution. But within the program synthesis community, there is a whole gamut of techniques, ranging from very formal techniques with very strong guarantees to techniques that potentially are able to scale better at the expense of weaker guarantees. And one of the, I think, most exciting areas these days is around how do you combine these more formal techniques with large language models to be able to really get the best of both worlds.
And so when you're combining a large language model and trying to have these really strong guarantees, it seems like maybe there needs to be some sort of like architectural change for these like LLMs to perhaps have that sort of intuition, or is it more like guardrails on the output?
There's many different ways of doing this, right? So one of the big results that we had early on was to develop something we called counterexample guided inductive synthesis, where the idea was that even in those situations where you really care about getting a verified output, right? And you care about being able to prove that the output satisfies certain guarantees, you can actually rely on an inductive synthesizer that doesn't know anything about verification, that all it knows is, here are some inputs and outputs, and from those inputs and outputs, please generate me a program that matches those inputs and outputs. And so using this framework, what you're able to do is create this feedback loop where the synthesizer produces some candidate program that matches the inputs and outputs that you have given it so far. And then you try to verify that program. And if you succeed, then it's great, you're done. But if you fail, then you can feed back into the synthesizer with concrete evidence for why this fails to satisfy the property, so that now the synthesizer can reason in terms of this concrete evidence. So it doesn't have to reason about the general case of how this program is going to behave on all possible inputs. It only has to reason about these concrete instances of how it fails on this particular input. And from that, by setting up this interaction with the verifier, you can actually get something that works very effectively. The key is, how do you provide that feedback to the synthesizer in order to guide it to produce a program that verifies. And one of the things that is actually quite interesting, initially when this kind of techniques started to become popular, the conventional wisdom was that synthesizing a program this way should be strictly harder than just the standard verification problem, right? I mean, how could it not be? In standard verification, somebody already hands you the program, all you have to do is prove that it's correct. How could that possibly not be easier than the case where you have to first generate the program and then prove that it's correct? But what the community discovered very quickly was that this is not actually the case, and somewhat counterintuitively, it's actually much easier to try to do synthesis and verification together than if somebody already hands you the program and all you have to do is verify it. And the reason for that is that no verifier is complete, right? What does that mean? It means that you can't build a verifier that for every possible correct program, it tells you that it's correct, and for every possible incorrect program, it tells you that it's incorrect, right? Such a verifier would solve the halting problem. So you can't build that kind of a verifier. So all verifiers have blind spots, right? They have, if you write your program in a certain way, the verifier is not going to be able to tell that it's correct, even if it is correct. And the problem is, if just somebody goes and hands you a program, even if it's correct, unless your verifier is very, very robust, there's a pretty high likelihood that this program is going to fall on these blind spots of the verifier, and the verifier is going to have to work really, really hard and potentially not be able to prove it correct. By contrast, if you're synthesizing the program and you can actually provide feedback from the synthesizer to the program generator, you can actually guide it to work around the blind spots of the verifier. So you can even have a verifier that's very weak, that has lots of blind spots, and you can still have the program generation work around those blind spots to find the right way to write this program so that the verifier has an easier time generating it. So there is actually a lot of really interesting technical insights that come from all of this pre-LLM work that is actually very applicable and very useful if you're trying to get LLMs to get you verified code, for example.
Yeah, that makes a lot of sense between like why making a verifier would be a lot harder than just synthesizing the program. I had a question along the lines of something more to do with AI safety. So like right now, a lot of companies are trying to create like evaluations, but those evaluations are like really hard because we don't know how capabilities of AI are going to increase in the future. So using program synthesis-esque techniques, do you think there's maybe a pathway to creating guaranteed safety for more advanced AI systems?
So it depends on what you mean, right? I think one of the challenges of AI systems is that they're so general and they can be used for so many things that it's very hard to provide some kind of universal guardrail that is going to guarantee safety for all the possible use cases of an AI model, right? And so if you focus on any specific domain, right? So if you say, well, I have this AI system that is specifically going to be used to help me write code, then you can bring to bear a lot of these techniques to actually make sure that the code that it produces is actually not going to have backdoors and is not going to have hidden vulnerabilities. One of the things that I think is very exciting today is we have the technology to build bug-free code, right? We have the technology to build unhackable systems where you can actually provide a mathematical proof that this system is impossible to hack. The reason why generally people don't do this in a production setting is because it's ridiculously expensive, right? It just requires order of magnitude more effort and some very expertise that is very scarce on the ground in order to build systems like this, right? But it is possible, and there are systems like this. And I think one of the actually really exciting applications for AI is if it can really dramatically reduce the cost of building this kind of extremely high reliability of software, right? But this is this is something that is helpful if you have an AI system that is building software, if you have an expert user who's managing it, who is able to establish those guardrails for the system, right? Now, is that going to help you if you're trying to build an AI system to do medical diagnostics? No, not really, right? That's the safety problem is just completely different. We don't really understand enough about even how to describe the safety property in that context to be able to say this is what it takes to get safety in that domain. So I think it really depends on specific applications.
Awesome. But yeah, I mean, I was also reading about some of your research in the past, and you were talking about deep learning regarding program synthesis. So I've read that like some of your recent work that's focused heavily on neuro-symbolic programming. I thought that was really fascinating. So I was wondering if you could give us a quick rundown about what that kind of entails and how it works for some people who don't know exactly what it is.
Sure. So, one of the traditionally, the way we have told computers what we want them to do is by writing code, right? And modern programming languages are this marvel of engineering that allows you to describe functionality with a level of precision and at a scale that is really unprecedented, right? There's a lot of things that are really cool about modern software development and modern programming systems, right? But there's also another way of telling a computer what it is that you want it to do, and that is learning, right? You go in, you show it lots of data explaining exactly what you want it to do, showing lots of examples of what you want it to do, and then you hope that the system learns the pattern and then does the thing for you, right? And that model has a lot of really good things going for it, right? It has allowed us to write applications that we didn't know how to write before because we didn't know how to describe them in code, right? If I want to go and write a system that distinguishes images of dogs from images from cats, right? We don't really know how to write that algorithm, but we can easily find, millions of pictures of dogs and millions of pictures of cats and just train the system and have it do it for us. And so you have these two ways of getting machines to do what you want, and both have some really important strengths, but they also have some really important weaknesses. And so one of the things that we want is we want machine learning that has more of the features of programming, right? That has many of the things that make programming useful and desirable. And, there are many, right? Things like modularity. When we write programs, we can say, okay, there's this routine and it's responsible for this. And there's this class over here and it's responsible for that. And there's this other class over here, it's responsible for that. You can define these very clear interfaces. By contrast, if you build a big neural network, it has layers. But we can't really say what each layer does, right? The whole point of neural networks is that you have these very distributed representations where you can't really pin down and say, oh, this and this neuron does this and this neuron does that. The explainability aspect, right? Being able to take a look at a piece of code and reason about what that piece of code is going to do, introspect on that piece of code, be able to bring the whole program analysis toolkit to analyze that piece of code and, for example, find corner cases that are going to get that code to do something undesirable or verify that it does the right thing. And so what we want to get the best of both worlds. We want to be able to learn this functionality strictly from data, but we also want representations that are interpretable. We want to be able to get the modularity. We want to be able to get the ability to introspect on what you learn. And this is really important in a lot of domains, right? There's a lot of domains where we don't really care, right? You trained your classifier to distinguish between dogs and cats. How does it do it? Who knows? As long as it works, and as long as it works reliably, and I can test it and make sure it works with a certain fraction of reliability, I'm happy. It's useful enough. But there's a lot of domains where you really, really care about understanding, where you really care that the model that you learned is consistent with prior knowledge, where you really care about being able to provide some guarantees about how this model is going to behave, even when you show it some example that is really different from anything that it has seen before. And so this is where these techniques can be very, very valuable.
Awesome. So from what I can understand, I think that neurosymbolic programming has a lot of potential positives and advantages to our current methods that we're trying to use to solve some real world problems. And you mentioned some test cases or like some potential simulation cases. But as we kind of explore more into this type of programming and as we see what kind of benefits we're starting to unlock, what do you think are some of the major problems or unsolved questions that we can potentially now approach with neurosymbolic programming that otherwise we just couldn't?
So I think one of the most promising domains is around scientific discovery, right? This is a domain where, on the one hand, the whole point is about understanding, right? There's debates can get a little bit philosophical around, what do we mean by understanding, right? Why does it matter so much that somebody just gets this warm, fuzzy feeling that you get when something clicks in your head and you say, oh, I understand that now. But it can have really practical implications. For example, one of the domains that we are working on right now is around biology. And in particular, we've been doing some work trying to understand the process of RNA splicing, right? Essentially how your cells manipulate RNA as it goes, before it leaves the nucleus and goes to help serve as a template to produce a protein. And so this is a domain where there's a lot of very hard-earned domain knowledge, right? Where scientists have been doing experiments for now, about half a century, where they have been doing experiments trying to figure out exactly how this process works. So we want to build on that knowledge. There is also a lot of data because it's nowadays possible to actually sequence RNA from the cytoplasm. And this essentially tells you, look, this is how the RNA looks like in the cell after it left the nucleus. So there is a lot of data. And so it is possible to just create data-driven methods. But you don't want to just ignore all of these half century of really hard-earned knowledge that has been gained through very clever experiments, and just say, oh, I don't need that knowledge now. I have lots of data. And you can use that data, you can train a model to make predictions, but making accurate predictions only takes you so far, right? Being able to predict, okay, well, if the RNA looks like this is how it's going to look like after processing, that's useful, but what you really want to know is why? Why does it look like that? after processing, right? What are all the molecules that came into play that manipulated it? How did they manipulate it? Because it's that deeper knowledge that is actually going to allow you to develop pharmaceuticals, for example, right? Just having some black box that tells you, well, if it was like this before, it's going to be like this after. That is not going to be as useful in helping you develop new therapies or new medicine than if you have a full picture of, oh, this is exactly how it's going to be manipulated, and this is exactly what happens step by step, right? And so this is where the neurosymbolic techniques can bring a lot of value, right, in helping you pry open that black box, in being able to incorporate some of this prior knowledge, and in terms of being able to get a model that tells you more than just, well, for this input you're going to get this output, and that actually is able to describe in some detail the underlying mechanism that connects that input to that output.
I think, like, based on my understanding of what you have just said, like, it seems that neurosymbolic programming is a very like data driven, also like very like heavy interpretability driven thing, like type of thing. And then like currently I've seen that, like, based on my limited research that I've done online, seems that like program synthesis and like neuro and like the field that you're working on right now seems to be like major big tech focus. So like, how do you think academic research, which is like traditionally more public, like can shape this industry that's like clearly privatized and like profit driven?
So that's a really good question, and right now we are in this situation where companies have access to a level of computational resources that in academia it's just not really possible to reach, right? And at times it's easy to feel like there's just this steamroller going through and flattening everything in its path. At the same time, industry is very good at, once it identifies a path, just running through that path and bringing in enormous amount of resources down that path, right? For example, for a while right now, the path was bigger models, more data, trained more intensively, right? And that was the path, and that was where everybody was competing with, right? But I think where academics have a really important role to play is in actually exploring some of these avenues that are off the path, right? And that have different qualities and different trade-offs. And yes, you're not going to be able to explore them to the same degree, but you have the ability to explore them much more freely, because you don't have the pressure of everybody's competing down this one path, and so everybody has to be super focused on making sure that we're going down the path as fast as we can. I think another really big advantage that you have in academia comes with interdisciplinary research, right? If once a company decides that it wants to go down one particular path, it can go and just hire unlimited numbers of the best PhDs in that particular area, right? As many as can be produced. But one of the things that you have in academia is just a diversity of expertise, right? In a wide variety of subjects, right? And especially when you're at a place like MIT, right? If I want to do something that connects with robotics, I can go down the hallway and talk to some of the top roboticists in the world, right? And when we started doing this work around RNA splicing, right? It turns out that MIT has not just one, but actually lots of faculty members whose core area of expertise is around understanding RNA and understanding how it's processed in cells, right? And a few years ago, for example, we started doing some work um in linguistics and actually applying some of our neurosymbolic techniques to understanding language, right? And again, there's a whole department full of some of the best linguists in the world. Um, and so this is something that no company can match, right? This diversity of expertise across a variety of subjects, and I think that is also the kind of research that is very difficult to do in in a company. Now, specifically when it comes to some of these neurosymbolic techniques, I think one of the advantages that they do bring to the table is that they are able to make up for they are able to leverage domain knowledge and leverage prior knowledge represented symbolically in the form of constraints or in the form of programs, and be able to leverage that in order to be able to learn more efficiently, right? And so actually there is also a computational advantage that means that you can actually do some really interesting things without requiring the kind of massive computational resources that only companies have access to.
I see. So like there are I see that like there are like various benefits as to like a wild professionalized academia versus like a highly commercialized company or industry. But like do you think in the future would like your group with MIT or like any other academia be like cooperating with, for example, Google, like to increase like the amount of like massive data that they have to like use for specific and more professionalized training?
Yeah, I mean there is a lot of collaboration between between universities and industry, right? It's not we're not antagonists of each other, and in fact a lot of the research that happens in academia informs what happens in industry, right? And some of my students, for example, who have trained in my group, actually went on to positions in industry, and to develop a lot of the technologies that are now becoming very popular, right? In fact, one of my students who graduated and went to Microsoft, Rishabh Singh, went to Microsoft research after graduation. After that, he worked at Google. After that, he worked at Meta. And in each one of these places, he developed uh, a lot of these technologies building on language models and leveraging language models for code generation. And he was one of the earliest people doing that actually in industry. So
Awesome.
it's not an
Oh, sorry.
antagonistic relationship, right? There's a lot of back and forth, and there's a lot of collaboration with industry. Industry itself recognizes that there's a lot of research that academia is uniquely capable of doing, and actually funds a lot of academic research.
That was a really thoughtful answer. As you know, Hack Club is a global community of high schoolers interested in computer science and mechanical engineering. And as a community, I would say we're probably more inclined towards having a really strong startup culture. And as you explained, academia and industry have a lot of overlap and they're symbiotic in their relationship. So I'm wondering, like, what's your advice for a high schooler right now in Hack Club who's maybe unsure if academia is for them, but wants to look into pursuing a career in it?
So I think one of the biggest things is uh, do you trying to get some experience doing research, right? And trying to uh, trying to build things that have never been built before. And I think one of the really, in some ways, building a new product or building a new company and doing academic research have a lot of similarities, right? And in both cases, you're trying to do something that has never been done before. You're trying to push that technology envelope to to try to get to that capability that has never been achieved before, right? This is where the really successful startups shine in being able to really have these capabilities that people just didn't think possible. Um, I think one really important difference between sort of startup mode and academic research mode is in startup mode, the end goal is the product, right? The end goal is the thing that works and that people can use and that spreads around the world. Um, in academic research, the product is the idea, right? And your goal as an academic is to uncover those ideas that haven't really been made before, and to prove that they work. And so, a big thing about that is going beyond just, okay, the thing works, we can now push it out, to, okay, the thing works, why, right? Why does it work? What happens if we simplify it in this way? Does it still work, right? And what happens if we simplify it even further? Does it still work, right? What is really essential about this thing that makes it work, right? And distilling that idea to the point where you can now take it out to the world as an idea, and people can then build on that idea and deploy that idea in their own context and in their own settings. And that is a really exciting thing, right? Ideas are ideas, if they're really good, and if you're able to explain them really well, they can have a level of impact that is just as large as that of a widely used product. And I think one of the things that characterizes research is this desire to focus on those ideas, right? And to really push these ideas to figure out, where do they break? What is the essence of this idea that makes it work in this way, right? And so, I think for people listening, if this sounds like something that really excites you, then you should absolutely pursue a research career. It's really a lot of fun.
That's solid advice. Thank you so much for your time today, Professor Solar-Lezama. We've had a blast learning about program synthesis, neurosymbolic programming, and also your insights into academia. And if anyone is interested in more of these conversations, look out for future AMAs on the Hack Club Slack channels, and you can join that at hackclub.com.
Thank you. Thanks a lot, and very happy to talk to you.